We are going to talk about Scotty, which is an operator for efficient window aggregation based on general stream slicing. So to give you a very brief high-level introduction, we are looking at stream processing pipelines, which is a series of concurrently running operators which continuously consume input data and produce output data. And within this pipeline, we look at one particular operator, which is the window aggregation operator. So what this operator does is basically it receives a series of tuples, then combines those tuples, here the numbers 3 and 5, to an aggregate, which is the number 8, and then they output that aggregate. So of course this is going to be way more complex if you have more complex aggregation functions than a sum, or more different window types, or more concurrent windows, or different queries, and so on and so forth. So what was the motivation for this work? We basically were looking at a series of Flink issues which were complaining about poor performance with sliding time windows, or requesting to improve the sliding time window performance, or just asking for lightweight event time windows. So what's the background here? I captured a piece of a description from one of those issues, and the point basically is that due to the bucketing approach you have in Flink, if you have a lot of overlapping windows, so in this example the user here writes about a 10-minute size window which slides by 1 second, this results in 600 concurrent buckets. So each tuple you receive is assigned to 600 buckets and gets aggregated 600 times, which is a huge overhead. So our idea was to overcome this limitation, and we have been doing some research on that at TU Berlin and also at KTH. So we structure this talk basically in two sections. The first part will more the conceptual background, talking about the stream slicing technique and our idea for generalizing the stream slicing approach to arbitrary window types and aggregation functions. And then the second part of the talk will be concretely on the Scotty window processor, which is open source, and you can use it in Apache Beam, Apache Flink, and Apache Storm with the different connectors we provide. So let me first give you a bit of the research background. We have basically 3 papers published on that, where you can get a more detailed description. The first was mostly led by KTH, which was the Cutty paper, where we looked mostly on the expressiveness with respect to the window types. Then we had the Scotty first Scotty paper at ICDE, where we focused on enabling session windows, but also looked into generalizing the approach for being able to process out-of-order tuples. And then this year we actually got the Best Paper Award at EDBT, and there we came up with this general stream slicing solution, where we basically allow all the different types of aggregation functions, windows, out of order, and we combine all this and basically automatically decide what's the best way of executing your window aggregation to get the best performance depending on what queries you have in the system. So all this is now available as Scotty window processor in our GitHub repository, and you can check that out. So let me give you first an introduction to the basic stream slicing idea. If you want to see that more in comparison to the bucketing technique, then also check out our last year's talk on YouTube, because there we do basically the side-by-side comparison to the buckets technique. So in this example, we have just 3 windows, so that would be the result of a regular sliding window, and you get those overlaps. The idea of slices now is to divide the stream in those non-overlapping chunks, so every time a window begins or ends, we also start a new slice, which means that the number of slices depends on your workload, so on the windows you define, not actually on the amount of input data you process. And that's quite nice, because you can very well predict how much state you need and how much you have to write to your state backend, so it gives you quite deterministic query performance. So when we now process tuples, we first receive a tuple, then we receive a second tuple, and as soon as we have 2 tuples, we can usually compute a partial aggregate. Here, the sum of 7 and 5. And we do that computation incrementally whenever we receive tuples, which means that if we can, we only store the partial aggregates instead of all tuples, which leads to a small memory footprint, and it also leads to a quite equal utilization of the processing power over time, since we don't have that lazy computation of aggregates at the end of windows. Another nice feature is that, as you can see, if the stream continues, we always assign each tuple to exactly one slice. So we overcome this limitation. I pointed out in the beginning of the presentation that we have this 600-fold or whatever time-fold ingestion to concurrent buckets, since we always only have a single slice. So once a window ends, we have to do a final aggregation step. So here in this example, we sum up the values 18, 11, and 6 to get the number 35. And this we can usually do quite fast, since there are seldom more than a few hundred slices. So this final aggregation step can be done in a tree structure, which even reduces the latency. But usually, even if you do that lazily, it does not expose a big latency. And since we can actually share the aggregates, we also basically have this low latency feature here. So now the point is, we need to be more general than just addressing the simple sliding windows with commutative aggregates and so on and so forth. So we have been doing some research on what's basically the general stream slicing idea. And if you look into our EDBT paper from this year, it's basically structured around what we call workload characteristics. And those workload characteristics are categorized into 4 groups. And the idea is to be general, to be able to address all those characteristics and to on the fly adapt based on what query you pose to the system, so that we always select the best way of executing the window aggregation in Scotty. So the first thing we look at is aggregation functions, and there we check if they are associative, commutative, or invertible, and we also check if they are distributive, algebraic, so that would be a sum aggregation on average, or if they are holistic. So in the paper we also show some advantages we can gain for things like quantile computations and median computations. So then we look into window types. The most easiest way are context-free windows, which is basically a sliding or a tumbling window where you can tell all the times when a window will start or end before even processing or looking at any tuple. But there are more complex types of windows where you need to actually look at the tuple, look at the data in order to decide did the window end or not. The most well-known here is a session window where you can only tell if the session expired once you have actually seen your data. The next thing we were looking into, or what we wanted to address, are the window measures. So we basically looked into the common time windows, which is what you all know from the standard Flink API, but we also looked into windows defined on tuple counts, and we support any arbitrary other time measures, so that can be any advancing value, be it, let's say, kilometers driven by a car or transaction IDs in your database. As long as it's something you can interpret as a timestamp, you can run it, and you can also run different window queries at the same time in a shared operator using one of them based on tuple count, one of them based on time, and one of them based on any other time measure you have in your input tuples. And last but not least, that's the easiest one, I guess most of you are aware of that we can have in-order and out-of-order streams. And if you can put the flag to your input stream that it will always be in-ordered, or that it's okay to drop out-of-order tuples, then in some cases we can do additional optimizations if we don't have to address out-of-order processing. So the nice thing about that general slicing solution is that it basically combines the generality of more complex or less performant solutions with the efficiency of the slicing idea in one single operator, without you having to think about, do I actually need the one technique or the other technique? So I want to give you another example to have a bit of an introduction into the impact of those workload characteristics on the actual execution of the window aggregation in Scotty. So let's look into the impacts of workload characteristics, and for this I just brought up a random stream of values here, and I picked quite small values so that it's a bit easier for us here to follow the computation. So let's define a simple count-based tumbling window where each window should have a length of 5 tuples. So what that actually means is that we have a time measure. Here our time measure is the tuple count, and with each tuple we receive, the tuple count increases by 1, here up to the value of 15, which is the end of our third window. So now the question we would ask is, first of all, let's see the slices we are going to get. So the incrementally computed results of the first window will be 11, then 13, then 12. And since we here have no overlaps, this exactly corresponds to the slices Scotty will keep. So now, what if the stream is out of order? And there, to think about this, we have to briefly check how is stream order actually defined. So this brings in yet another timeline, which here is the event time, and we have some event timestamps here which define the order of the tuples in the stream. So what happens now if we receive an out-of-order tuple? So here we can receive a tuple which has the timestamp 49, and it actually has the value 5. So this tuple needs to squeeze in our tuple count between the 9th and the 10th window, which actually means that all the tuples have to shift by 1, and then we can squeeze in that value 5 here, and all the counted tuples which we have from later results now basically have an increased timestamp on the tuple count time measure. So what we now need to do is we need to update those two slice aggregates in order to still be correct, and we do that by basically updating those aggregates with an incremental aggregation step. One thing you can see here is that since you use the window based on tuple counts and you said the stream may be out of order, Scotty knew that we have to keep individual tuples in memory in order to be able to recompute aggregate results. So that would be something the framework would have detected. And since we have a sum aggregation, we know that this is invertible. So what we can do is we can perform the shift here at the value 5 and then incrementally update the first slice by adding 5, removing 3, and updating the next slice by adding 3 and removing the number 1. So since this is an incremental computation, we can perform that update quite fast. So now the next question would be, what if the aggregation function is not invertible? And you see how this continues basically to a decision tree where, depending on the different query characteristics and the stream characteristics, you can end up with quite different ideal executions for your window aggregation. And if you look to our stream slicing paper we had at EDBT, you will find exactly those decision trees which describe how Scotty, depending on which windows you post to the system or which query definitions you post to the system, adapt to those workload characteristics. So with that, I would like to hand over to Philipp, who will present the Scotty window processor based on the code and give you a bit more of an introduction on how to use this in your Flink jobs.
Yeah, thanks. So as Jonas already mentioned, I will now introduce to you our window operator, which you can basically use in your Flink, Deem, or Storm pipeline. So let's start with its key facts or core features. So our window operator is a basically standalone window operator. It has no dependencies to Flink, to Beam, or to any other framework. So you can embed it easily in whatever system you use. And you could also use it completely without any stream processing system, just as a Java library to which you pass tuples and process window aggregates. So what it gives you is that you get high-performance window aggregations with this stream slicing technique we presented earlier. And you then can scale to thousands of concurrent windows. In this case, I mean concurrent windows, which result, for example, from a sliding window, which is huge size and a small slide. However, concurrent windows can also result from a query which has multiple window queries on the same stream. So you can imagine that you have the same source stream and you want to do a window aggregation with a sliding window, with a tumbling window, and with a session window. And Scotty can reuse the aggregates, and yeah, your performance will benefit from this. And furthermore, Scotty covers all the different window types, aggregation functions, window measures, and the stream orders we discussed earlier. So what our repository also provides to you is our connectors for Apache Flink, for Beam, and for Storm, such that you can easily embed this in your hopefully in production running pipeline, and we will even develop more connectors in the future, for example for Spark, and so on. So let's now get a peek into the architecture of Scotty. And here we see basically our input stream, for which you have to define the stream order. So do I expect out of order tuples or not? This stream is then passed to the Scotty window operator, which then maintains the slices and in the end produces the final window aggregates. To do so, it uses your window definitions, which always consist of this workload characteristics mentioned by Jonas, the aggregation function, the window measure, and the window type. With all this information, it always then can choose the most optimal solution or way to process your window aggregates. For example, if it has to drop tuple or if it has to keep tuple in memory. What is also interesting is that these window definitions don't have to be static during the runtime. So you could also manipulate window definitions during the execution of your job, which is another feature we will investigate in the future. Based on all this information, we generate and trigger windows. And to define your own window types and window functions, we give you extension points such that you only have to implement simple interfaces, and Scotty will always choose the most efficient way to produce the windows. So Scotty adapts to your workload characteristics and combines the generality and efficiency in a single solution. So let's now dive into some benchmark results. So here first we see results for the built-in window operator of Flink, Storm, and when Flink is running on Beam. What we see is that the poor window, or the native window implementation of a Flink performs really well when we have a tumbling window or a window with only one concurrent window. However, when we now have different or more concurrent windows, for example, when we have a sliding window, then the performance of Flink drastically drops. And what is interesting to see is that for Storm, this performance is always staying constant because Storm is using a different windowing technique, which always keeps all tuples in memory, such that it can process sliding windows a bit more efficient. However, when we now see what changes when we introduce Scotty is that now for all systems, the performance is independent of the number of concurrent windows. And even for Storm, the performance increased because Scotty is a more efficient window operator than the native Storm implementation. So how can you use Scotty in your Flink pipeline? First, you have to clone our repository and add it to, build the Maven dependency and add it to your local Maven repository. Then you have to basically add your Maven or our library to your Maven project, and then you can basically use it just as a new operator in your pipeline. You just have to initialize our window operator and pass your aggregation function. Then you can add any number of window definitions. Here we have a tumbling, a sliding, and a session window. We gave the window measure and the time, for example, 1000 milliseconds in this first case. And then we add this to our stream processing pipeline via a processing function. So this is basically standard Flink. You don't have to change anything more in your pipeline. You can just use it. So it's pretty easy. And therefore, I would now like to wrap up. Scotty provides you a high efficient window operator, which you can easily connect in your Beam, Flink, or Storm pipeline. And we would be really happy when you try it out, when you contribute to our repository and gave us feedback. And I think now we have still some time for your questions. Thank you very much.
So this sounds amazing. Why isn't that part of the Flink native core library? Why ever use Flink native instead of this?
Yeah, so 2 points. First of all, we are researchers and need to publish papers, so the focus was on getting research accepted rather than making pull requests. The other point is that Flink offers you a lot of features which we do not address in this implementation, which is, for example, in Flink we have side outputs in Windows, right? And those side outputs we did not yet cover in this general solution. Also, you have some ways of having custom triggers and evictions, which is also not fully covered here. I think it could be done, but it is a lot of work needed to implement this in the connector to then have basically a one-to-one mapping between the Flink operator and the Scotty operator. Another point is that our aggregation functions have some properties. They implement these interface, which, for example, have an invert function and so on. So if you think about how the reduce function in Flink looks like, it's not so easy to directly translate that to an aggregation function, which lets Scotty know about the properties of that aggregation. So it's not actually a one-to-one mapping between the aggregation implementation you have in your Flink aggregate functions and you have in the Scotty aggregate functions. So that makes it quite hard to basically just replace the Flink core window operator while keeping it compatible.
Yeah. So I was wondering, how does the system know whether, like, let's say, one of your aggregation functions is invertible or has some of the characteristics that you mentioned that allows you to actually do the optimizations? Because, I mean, these are black boxes in some way, right?
So what we do is basically that every window function implements a set of, or can implement a set of interfaces, which basically tell our system, our framework, what properties this window function has. For example, invertible, and so on. So
if you implement an invert function, then your aggregation is invertible. If you don't, it's not. That's basically the... Yes.
What sort of aggregators does Scotty support out of the box? For example, max, mins, countdistinct. How do you handle that?
I don't have a full list at hand. I mean, we have basically all the standards like count min, count max, minimum, maximum, sum, averages. We have some quantile computations based on red-black trees. We are constantly looking into new. So I think it's like 15 or so, which you can find in the repository.
And then, what we are currently also investigating is to add more aggregation functions. For instance, there's just one project where we try to investigate sketches on top of streams, where we use then also Scotty, or where's the idea to use Scotty. And then the repository would benefit from these aggregation functions.
All right, thank you. One last question, which is, how does Scotty interact, for example, with RocksDB for state backend management?
So this is currently a part where we still probably have to optimize, because currently we just use the value state and pass the Scotty as an object we serialize there, which is not optimal. And this would also be one part where we would be really happy when somebody would show us their production work cases and try it out, and then we see, okay, these are the things we have to improve on, and therefore we would be really happy about feedback.
Yeah.
Okay, thank you.
I think here the major point is that the connection to the state backends has to be done for each system individually. So one needs to do it for Beam, Flink, and Storm. So that's basically individual for each connector to implement the state backend of the particular system. So we didn't do that yet to full extent.
No.
I think we should wrap it up here, because it's 5 minutes before 4, before the next talk. Thank you very much.
Thank you. Thank you too.